Okay, so we're talking about functions for today. The official title is called Interpreting Graphs. So on your notes, write down today's date, which is not 9/11 anymore, it's 9/12. So glad we made it through 9/11 without any major attacks. I didn't miss one today.
They're trying to trick us, and they're going to do today.
It's possible. I don't know. There was chatter that they picked up, credible threats, blah blah blah, that they were planning a major terrorist attack on the 10-year anniversary. They know Osama bin Laden had said that he wanted to do another attack on the anniversary. So I guess the good part is that we stopped him from what he wanted, because they didn't get one. But who knows? They might be planning one right now. But uh, basically, we made it through the anniversary, thankfully. All right, so today is 9-12, so you put that on the top of your paper, and then interpreting graphs. If you look at this graph and its website hits, I have a website, so I can relate to this. My website is called 2-Minute Teacher, and we do little 2-minute lessons. I've recorded about 1,000 of them that cover every math topic that you'd ever need to know, from kindergarten all the way through the end of algebra. And anyway, that website, sometimes we look at the hits on it. How many hits has it been getting this week or last month or whatever. And if you look, this one is not my website, but this one gets a lot more hits than mine. But generally, does it look like the trend is up or down? Up. Okay. And if you smoothed it out, there would still be 3 major spikes that seem to be kind of important. Now, if it's a website, why would you all of a sudden have a spike in hits on a certain day? Why would all of a sudden an extra 25,000 people come to your website on a given day? Something happened. Maybe a news story? Like maybe the website sells, I don't know, gas masks or something, and then there's a news story about how the terrorists were planning on using poison gas or something. So all of a sudden there'd be this big spike in sales because, or not necessarily sales, but at least visits, because people were all of a sudden really scared about poison gas attacks. Right? It might be a spike because of advertising. Maybe on those days they ran pay-per-click ads. I've done that before with my little business. It's kind of cool. If I want to sell a DVD in Georgia tomorrow, pretty much guarantee you I could sell a DVD in Georgia tomorrow, because I just set up the pay-per-click thing to only advertise in Georgia. And everybody who goes on the computer, I can make it so that pretty much everybody who goes on the computer in Georgia tomorrow sees my ad. It costs me a lot of money, but then I would probably sell a few DVDs out of it. So it's interesting how you can target it that way. I can pick a city. I want to sell a DVD in Atlanta, and then I pick the city. I set my price that I'm willing to pay per click, and then anybody in Atlanta who actually sees my ad and clicks on it, goes to my website, I have to pay per click. And a typical deal is that you pay like 25 cents for them clicking on your ad. And then they come to your website, and then you hope they buy your DVD. So anyway, it's kind of cool how you can target it that way. So maybe they did some advertising. Maybe Oprah mentioned it on their show. All it takes is a mention from Oprah to sell like 1 million books. Isn't that amazing? So if you're like an author and you make about about $1 per copy when you sell a book, that's just a rough number, but let's say that you make $1 a copy, and Oprah mentions your book, you sell an extra 1 million books. She can make somebody a millionaire just by saying, you guys should really read this book, 2-Minute Teacher or whatever, and poof, tons of people go buy it because they trust her, and I think the person can be an instant millionaire because she says their name. Isn't that amazing? Okay, this is another graph of the same data. Doesn't it look totally different? But if you look at the numbers, it still starts out around 2,000. It still ends up around 10,000. But it's averaging it out. And it puts it in little bins, like each month gets averaged. The average for the month then gets put all the way across there. Which one's more accurate? The first one or the second one? First one's more accurate. But the second one might be a little bit easier to read. And it kind of smooths it out, and those little spikes are less noticeable. But those spikes are kind of important because if you're a business, don't you want to know that when you advertised, you got business? I mean, you want to know that. That's kind of good data to have. So maybe a combination of the two would be good, where you have the average over time, and then the spikes are still in there to sort of remind you that those were the 3 big times we advertised, and we got lots of hits then. So, all right. If you're interpreting graphs, sometimes they're, we're just going to start with a really simple one. You have to know what you're talking about. We're talking here about a stadium and people leaving after the game. Anybody watch the Vikings game? So was it a good game? I know it's kind of a depressing ending because they lost, but did we have any bright spots in there? Yes. Seriously? Oh my gosh, I didn't see anything about it. So awesome. So Percy gets the gold star. How about our new quarterback? I think I heard bad things about that on the news this morning. Oh, intercepted on his first throw. Ouch. Okay. Well, anyway, so picture at the end of the day, there's people in the stadium, right? And then they leave. So there's a lot of people at time 0, which is right time since the game ended. So at the very end of the game is right here. So this is time since the game ended, and let's say that that's 30 minutes later. There's pretty much everybody's gone after 30 minutes. Okay. Do you think in reality it would be a flat line like this? No. I'd like you on your paper to make a little sketch of what you think a more realistic graph would be. It wouldn't be a straight line like this. Show me what you think if they actually graphed how many people are still left in the stadium. What would it look like for 30 minutes after the game ends? No, pause while you do that. Well, there's basically 2 ways you could go with this. You could either say time and peeps. Starts up here. Does it go down fast or slow at the beginning? What do you think? Really fast, right when the game's over. Why does everybody try to leave so fast? Get out of the parking lot. Yeah, the traffic gets really bad, really fast. If you wait too long, you get stuck in one of those ramps for like half an hour or so. All right, so there's a lot of people leaving really fast, and then what? And then from after that, it probably slows down, and maybe it goes down like this. Maybe it goes, I don't know, more like this. You know, it depends on the exact data. Would you say that there's probably, after half an hour, still some people in the stadium? Yeah, not many, you know, but, and what would this mean if you had, it's going down, and I know some of you are also more accurate because you like made little jaggedy things, but if you made your little jaggedy things, you never want to actually go up unless you mean that the number of people in the stadium is going to go back up again. Is that possible? Yes. Why could there be all of a sudden, you know, maybe we'll just make one blip up at the end. It goes faster, slower, faster, slower, faster, slower. It makes sense, but you don't really want it to go up. But let's say it goes back up a little bit at the end and then back down. Why would people come back in to the stadium? Yes. All right, they're coming back in for the next game, all right? And then maybe not that many people would have left if it was a doubleheader. But maybe they would go get, you know, refreshments or whatever. Yeah, people forget stuff and they come back in for it. Yes. Okay. Yeah, it's a good point. It doesn't have to be like, this is people. It doesn't necessarily mean, maybe some of these are like workers that come in to clean up the field and stuff. Good point. All right. Independent versus dependent. Write this one down. This is like some of the meat of what you need to write. On the left side, on the up and down, that's dependent, and put money, and also put, this is where the range is found. The range is up, down. The independent variable goes in the bottom, and time is the ultimate independent thing. Time is always independent. So if there's ever a choice, like which one of these is independent, if it's ever time is one of the choices, pick that, because time is independent. And the last thing is the domain. The domain are the inputs, or the things you put in, and the time is like an input. So when you're graphing something, time is the ultimate independent thing because it never stops. It only, well, if you were Einstein, Einstein theorized that time could be bent and that there could be something called a wormhole. So I'm holding a piece of paper for those who can't see this. Time is like usually thought of as linear like this, like time just goes on. But if you can bend time, then you could also bend space. And all of a sudden you could be here and here in time and in space, and they could change and touch so that you could be in two places at once, so that you could theoretically travel vast distances like across the universe through I think I've heard it called an Einstein-Rosen bridge, which is another name for a wormhole. I think caught on because it was snappier. But the Einstein-Rosen bridge might say that time could stop. But we're going to say that time keeps going forever. And money is the ultimate dependent thing because, for example, what does a hot dog cost? What's the cheapest you've ever seen a hot dog for sale for? I've seen it even cheaper than $1, but I'll believe you. $1.50 easily. Okay, I've seen them for 50 cents a fair amount of times. Really, if you go to Cub Foods during the day, they a lot of times are running like a special. So you can get 2 hot dogs for $1 at where is it? At Super America, I think they have those. So they can be as cheap as like 50 cents for a hot dog. And if you actually go to Cub and you buy a package of their cheap hot dogs and a package of their cheap buns and you average it out, you can get them for like $0.25. Okay. So hot dogs can be as cheap as $0.25. But the price is dependent on where you are. You take the same scenario you're at the baseball game and say how much for a hot dog, and what are you going to say then? $4 probably, $4.50 maybe even $5. And then they'll like upsell you to the super dog, which is like $6.50 or whatever because it's really big. And I actually had one of those down in out in South Dakota, and they had this they call it like monster dog or something. The thing was insane. It was like 6 normal hot dog size. I mean, it's just huge. And when you ate that thing, you're just stuffed. But it was really good too. They made it out of some kind of good cuts of beef. And anyway, so how much does a hot dog cost? It totally depends. It will fluctuate up and down a lot based on where you are. The last one would be, do you think that a billionaire who's traveling across Africa and gets lost, separated from his group, and he is in the desert and he is now dying of heat exhaustion and he needs water, he's dehydrated, you think he'd pay you $100 for a glass of water? Oh, absolutely. He'd probably pay $1,000 if he was in a good mood, unless he's just too stubborn and willing to die because he doesn't want to overpay for the water. But depends, in the right circumstances, people pay a lot for certain things. So, all right, moving on. So of these 2 combos, which is independent? The first one should be a no-brainer. Time. Because time's always independent. Time's the ultimate independent thing. So if you're looking at time versus temperature, we'd put time on the bottom. All right, if you're setting up a graph for ice cream sales versus temperature, which one should go on the bottom and therefore is independent? Temperature. Do you think the temperature decides how hot to be based on the ice cream sales? Like, ooh, they sold a lot of ice cream. I better warm up out here. No, it doesn't work that way. But do you think ice cream sales depend on what temperature it is? Yeah, if it's a really hot day, more people go out and buy ice cream. All right. How about the cost of food versus the location? Obviously, something depends on something. Which one depends on the other one, and therefore the other one's independent? Which one's dependent? Cost of food depends on the location, right? So therefore, this one's the dependent one, and this one's the independent one. Get that? So sometimes the easiest way to figure out what's independent is to figure out which one depends on the other one, and therefore is dependent. And if you know which one's dependent, you can tell which one's independent. All right, moving on. Increasing versus decreasing. This is just the really quick broad strokes on this. Is this increasing or decreasing? Increasing. How about this one? And how about this one? Well, don't be fooled by the arrows. It's decreasing and then increasing. because you read from left to right. So this arrow right here is kind of deceiving. You read from left to right, so you'd say it starts out decreasing and then it increases. All right, how about this guy decreasing? Why is it different than all the others? It's linear, and therefore you'd use a different word about how it's decreasing. It's decreasing at a certain rate. How would you say it? A constant rate. Very good. This is going down at a constant rate. Notice this was decreasing, but it's not at a constant rate. So then there's two kinds now that you have to say. When you look at a problem now, you're going to be asked to say, okay, easy, it's increasing. Easy, it's decreasing. But at what rate? You'd say it's increasing at a constant rate. What would you say about this one? Decreasing at a constant rate. How about this one? Decreasing and it's not constant, is it? So it can be weird. You can say something is decreasing at a decreasing rate or decreasing at an increasing rate. So what's this? It depends on the steepness. Notice here it's not very steep versus here it's very steep. So its steepness determines the rate. So the steeper equals faster. Would you please write that on your paper? Steeper equals faster. Because when you get stuck on these, you got to fall back on some rules like, I can't remember what he was saying, but if you can remember, steeper is faster. This one starts out going not very fast, otherwise known as slow. And this one ends up going really fast. So this one is decreasing at a what? At an increasing rate. Yes? Good point. We aren't going to use that term, but you are correct that at least this would be increasing exponentially. But what you'd need to find, it's a multiple choice test, I think, is increasing at a what? No, I wouldn't say faster. It is going faster and faster. Yes. Increasing at an increasing rate. All right. This red one's doing all kinds of crazy stuff. Is it ever decreasing, the red one? No. So it's increasing at a variable rate. Okay. And it starts out increasing kind of slow. And then it actually looks like it goes flat, which would be constant. And then it's increasing at a increasing rate. And now it's increasing still, but at a what? At a decreasing rate. So any individual graph can have lots of little parts that are going at different rates. All right. So how would you demonstrate increasing? It's just got to be going up. Decreasing or going down as you read from left to right. Slow change, what would you say about the graph? If it's going slow, it's not very steep. And if it's fast, then it's steep. And if it's constant, what kind of a line will it be? A straight line. Straight lines are constant. Now, just plain constant is something different. That's where you got your graph, and the thing you're looking at is just going straight across. That is called constant. It's not increasing. It's not decreasing. It's not increasing at a constant. It's not decreasing at a constant. It's just constantly constant. All right, so constant, just the word constant means this. Again, this is got the word constant in it, but you'd say what? Decreasing at a constant rate. Okay, so now, when should you use a straight line? When things are going at what kind of a rate? A constant rate. When should you use a curve? It's either increasing or decreasing. Good. All right, good. And now, if you're going to do increasing at an increasing, I know it goes up. Is that increasing at an increasing? That's increasing at a what? Constant. Is this increasing at an increasing? No, that's increasing at a decreasing rate. That's what we'd want down here. This one, what we want, increasing at an increasing would be like that. All right, and increasing at a steady rate, otherwise known as what kind of rate? Constant rate would be like that. All right, moving on. I don't think we need to do that. Write description for the graph below. starts out doing what? It increasing in constant, and then it goes to just constant. All right. Students at school are complaining the pop machine is frequently empty. Several student council members decide to study the problem. They record the number of cans in the soda machine at various times during a typical school day, and they make a graph. All right, see the red line there? It's kind of faint, I know, from the back, but you see how it starts out up here at full? And it's full for a whole hour until 7, and then all of a sudden, what happens? It goes down. In the real world, what's happening? Somebody's buying pop. Okay, and what happens right here that makes it go up? It must have refilled it. Okay, and it's full again. And now what happens in this part? It's crazy going down. Why would that happen? Lunchtime, so everybody buys pop, and all of a sudden the machine's empty. And then they refill it, but what? But not completely. Okay, and maybe that's because they just didn't have time. You know, they were like hurrying putting in the cans because they wanted to like let people buy some more. And so I don't know why they didn't refill it all the way, but they didn't. And then some people bought more pop, and then it's empty again at what time of day? Into school. And then filled it up. And then there's kind of a slow drain to the end of the day because why are people here at 5? Teachers are leaving, sports are ending. Yep. All right. So, these questions seem pretty easy last hour, so I don't know if I'm going to do all of them. Based on the graph, at what time is the soda consumed most rapidly? Now, it's the steep parts, but there's a tie, actually. There's lunch and what other one? And into school. At both times, it appears that the machine is probably going about as fast as it can. Have you ever been to like a rest stop when a bus gets there and there's a big line for the pop machine and everybody's standing in line and the pop machine is just kind of constantly spitting out cans of pop? Next person goes, sticks in their money, and then their dollar bill won't work, and then they got to trade with a friend, and they, you know what I mean? Like there's this long line and it just keeps pumping out pop, 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 pop. So, all right. Do another one of these application ones. When is the machine refilled? How can you tell? Oh, that's too easy. The only time it's going to be refilled is if the line's doing what? Going up. Increasing is the official name for that. When is the machine empty? Duh, when it's at 0. What do you think the student council recommend to solve the problem? In other words, the machine's getting empty a lot. Is there any way to fix this? Yeah, get another machine. Good. Or a bigger one. Good. Good answers. What if those are both too expensive? Refill it more often, like maybe right in the middle of lunch they schedule a refill and fill it all the way next time. Yeah, that's a good idea. All right, good enough. Did you notice that our school pop machines don't have the kinds of pop in them that you get like at mall or whatever? I don't know if you even noticed that. If you look at the machines, they don't sell like regular Mountain Dew in there and fully sugared pops, because they think that you guys are getting too fat, and so they want to give you a healthier alternative, that kind of stuff. So, anyway, I don't know. I'm a little nervous about some of these changes that they're talking about. They're talking about some of the food in the cafeteria. They have to like have no salt in it now because that's supposed to be bad for you, and so if it's they got to decrease the sodium by like 40%. So I'm a little nervous that they're going to try to make things so healthy that nobody will eat them anymore. And but who knows? I hope that it'll just be accepted and people will like it just as much. I personally don't have a problem with having, like, some people have to watch out for how much salt they have because they have like high blood pressure and things like that. And I have actually kind of low blood pressure, and so I'm not that as worried about salt as some people are. Anyway, so I'll probably just grab the salt shaker. A lot of everyday information comes in the form of graphs. I'm reading the highlighted part here. If the reader can understand them. However, research carried out by the Shell Center in 1980 showed that very few pupils age 11 through 16 knew how to interpret graphs. All right, so basically that's supposed to be a weakness of people in general, is reading graphs thoroughly. So it's a good reason to kind of do what we're doing right now. And I think we've beaten this pop machine thing to death, except for one other thing. Technically, the graph should look like this. Because every time you sell a can of pop, it goes down exactly one can. This drop should be down one can. Now, actually, this graph isn't great either. Whoever made this one, because they have it going down and not exactly one each time. But the point is, it had a full machine, and then at one instant, it went from full to one less can of pop, right? You get that? If let's say it held 100 cans, now it's 99. It's a drop of one hole. It doesn't act, it goes ka-chunk right there. So the graph shouldn't really have a smooth line, should it? Because it doesn't go to like, okay, now we got 99 and a half cans, now we have 99 and 0.2 cans, now we have 99 cans. It doesn't do that, it's all at once, boom. So this kind of graph that shows the little drops, that's called a discrete graph. A discrete graph is more accurate because it's going to, be more exact about how it had 99, now it's got 98, now it's got 97, and it won't have this smooth line, which just is meant to help us read it. But a lot of real-world situations don't really have a smooth line. One thing that usually does is temperature. The only time I can think of a really sharp change in temperature, like dramatic within a 1 second period of time, is like when a bomb goes off. The nuclear bomb causes the temperature to spike to like 3,000 degrees in like 1 second. So yeah, that would cause a spike. But if you're just looking outside at the temperature, right now it's going to be like mid 80s, and it's tomorrow. You guys probably know this is dropping to 70, and then the next day it's dropping to like 65, and then the next day it's like 60. So we're going to go down from 88 today down to 60 as a high in a few days. So if you like the warm weather, enjoy it for the next day or two, because it is going to start to get cold, which kind of stinks. I don't think it's going to stay that cold, but we're going to have a cold spike. But even then, a spike doesn't drop dramatically. It's smooth. Temperature changes kind of smoothly outside. In fact, if it ever changes dramatically, you really notice it. Like, have you ever been outside and all of a sudden it was warm, and then all of a sudden it's like, whoo, that's like cold all of a sudden. You notice it if temperature changes fast. And that's probably only like 5 degrees, and you'll notice it. Because normally it changes so slow, you don't notice. Okay. This one I'm kind of interested in you doing, the temperature of a hot drink sitting on your desk. Would you make a little graph, like one of these little dealies, and think it through? What is the temperature going to be? Start it out at, let's say that the temperature is at 150 degrees. Here is this coffee. I'd like you to make me a little graph and see if it does this, or if it does this, or if it does this, or if it does that, or what. Make me a graph. If it starts at 150, of what the coffee would do sitting here on my desk. And while you're sketching out that little graph, I've got a little story for you. Did you ever hear about the lady who sued McDonald's because the coffee was too hot? She had dropped it in her lap and in the car, and it burned her bad, and she was old, and she sued McDonald's for having coffee that was hot. Now that seems completely ridiculous until you hear the rest of the story. It turns out McDonald's had been warned many times that their coffee that they were serving was illegally too hot, extremely hot. Like it was like 200 degrees or whatever. It was extremely hot. Now, why would McDonald's make coffee that was extremely hot? Because it was cheaper to make. They could make it with way less coffee grounds if they make it at super hot temperatures. So the way the jury saw it was that McDonald's was choosing to run their coffee machines really hot because they wanted to save money. And so this old lady who gets the coffee dumped on her at this temperature, which is hotter than what people say coffee is supposed to be, like the legal limits or whatever, felt bad for the old lady because, you know what, they were only doing it because they wanted to save money, and they cost her scalded legs. And so they awarded her, and they decided when they were in the phase of the trial, how much do you give the lady for getting burned? I think they gave her the equivalent of 1 day's profit on coffee for the year for McDonald's. But McDonald's is so big that that's like $2 million. So These numbers are all off a little bit. I'm rounding here, but you get the idea. They decided, okay, McDonald's, you're going to make all this money on coffee by running their machines hotter than you're supposed to, and we're going to penalize you for that. So sometimes there's the rest of the story. Okay, hopefully you have made your graph. Did you go like that? Okay. Some people have that kind of a graph. So I didn't see many heads shaking. Did somebody go more like that? Okay. Saw some heads shaking yes and some saying no. What's one piece that you think I'm missing here that I'm not doing right? Yes. Ah. Because room temperature's around 70. That's good thinking. So we could argue about how you get there, but let's say we get to 70, which is like right here. It better like level off, right? Because it's not going to get colder than the room. It's not going to eventually get to be freezing sitting on my desk there, right? That doesn't make sense. So here to here, though, I don't know. You could argue about how I haven't actually seen the graphs on this. It might cool. I would get the feeling that it would cool off fairly fast, because it's the difference in temperature between the room and the coffee is pretty big. And so I think it would go fairly fast at the beginning and then maybe slow down a little bit at the end. So anyway, one main thing that I wanted you to notice was that it stays at room temperature, which is 72 degrees, by the way. And the school keeps it around that. Of course, it's always either hotter or colder, depending on what room you're in, but 72 is kind of like the ideal. If you're in Germany, it's about 22 Celsius. That's right. Some of you are thinking, like, what? They all sit in the freezing cold? No. It's 22 Celsius. So if you're ever hearing that the temperature in Germany today was 25 degrees, was that warm or cold? That's pretty warm. Okay, because if you have an anchor point, like 72 is 22, that helps you to be able to say, oh, well then 73 would be like a little more than 22, like 21 and a half or whatever. No, wait a minute, more than 22. 22 and a half. Okay, anyway. So, moving on. Yes, sir. Celsius to Fahrenheit conversion. It goes like this. 9/5 F plus 32, I think. Or is it 9/5 C? I think it's 9/5 C plus 32. Because what you do is you have to think of it this way. At 0 degrees Celsius, it's the same as what? 32. So this is a good example of a function. Okay, and if this is 0, Celsius is 0, then Fahrenheit would be 32. Okay. One more thing on the topic of functions. Generally, since these are all functions that we're graphing, I want you to know a few things about functions. When I say this, that is function notation. If I say this, like 2x plus 3, that is the function rule. It doubles whatever you have and adds 3, for example. A function should be such that if I put in a number like f of 2, and I'd get 2 times 2 is 4 plus 3 makes 7. If I stick in a 2 and I get 7, then if I stick in a 2 again, it seems totally obvious. If I stick in 2 again, shouldn't I get 7 again? But some things that are not functions look like they're functions until you do that, and you see that f of 2 has 2 different answers. And you stick it in the second time, and it comes out to something else. Well, then it wasn't really a function. And that means that on the graph, let's say it's something like this. F of 2 would be like 2 is like the x. Remember how the x numbers are down here? And they're the inputs, and they're also known as the domain. If I stick in a number like 2, I better only get one thing out, because if I get something else out, that means the graph must be doing one of these kind of a numbers, which it's not supposed to do, because then it's touching twice, and it passes or fails the vertical line test. So this graph right here would pass the vertical line test. Here's a vertical line, close anyway. And notice it never touches it twice if I run a vertical line across it. But if I have a graph like this, a lot of people don't know that a circle is not a function. A circle is not a function. Why? Because it doesn't pass the what? the vertical line test. See how it touches in two spots? Only on the edges. It touches once there, touches once there, but every other place it's not a function. So, all right, so there's some notes on functions, things you're supposed to know. And now I got your assignment, which is about graphing. So I'm going to give you that worksheet.